fellow South African learners. My name is Ehlanzeni from Ehlanzeni College. I am lecturing in engineering, where we are offering electrical infrastructure and construction. The subject is electronic control and digital electronics, level 4. So our topic is a continuation of the last topic, which was on transistor amplifiers. So now, since we know how to analyze all the information on basic transistor operation, now we shall look at what we call the basic design of transistor amplifiers. Basic design of single stage transistor amplifiers. This is the basic design of single stage transistor amplifiers. So, like we saw last time, we only have an operating transistor as an amplifier under a linear, or what we call an active region. So, once we have our linear, or in the output characteristics, we shall have our output voltages, our output current. So, in that, we are only concerned with what we call the active region. The active region. This is our active region, where we can manipulate, where we can change, where we can vary IP such that it is below, or it is above cutoff, but below the saturation. So this is typical an output characteristic of what we call a transistor. So for a basic design, we need to know what we call a load line, a DC load line. A DC load line is a line on the output characteristics of a transistor circuit, which gives the values of the maximum current that can be allowed in that circuit and the maximum voltage that can be measured or can be given by that circuit, corresponding to an input signal where there is no external input signal. That is to say, our amplifier, it's on its static condition, or what we call DC conditions. So we now understand when we talk of a DC or static condition. An amplifier has got an input from a DC, has got an external input from an AC source. So now, there is this line which we have talked about, which I've said it's a load line. It's a combination, or it's a relationship between these two values. This will tell us the parameters or the expected values of the current at a given voltage. So it is ratio of the relationship in that two values. So now, let's see how we draw a DC load line. We normally just don't draw a DC load line like that. There are some calculations that are involved there. First of all, for us, we must know how our circuit is designed. Let's use a common emitter amplifier, a basic common emitter amplifier. A basic common emitter amplifier. And I will say this will be my plus VCC, RC, IC, okay? I will say this is IP. It must have some kind of a gain. The transistor will have some kind of a gain. So now, looking into that, we still need, oh sorry, there's one article missing here. Yeah, it's RP, our biasing transistor, RP. They'll be all connected to VCC plus VCC and grounded there. So now, In this amplifier circuit, we need to determine all these values so that we can simply design a single stage output amplifier. So for us to do that, we need to know how to draw the load line, the operating values. Remember, we said it can determine, we can predict the values along this line as long as we know those components which are supposed to give us those values. For instance, now, for us to determine IC, you see this is our IC here. This is our IC. How do we do that? Let's say when IC, let's start with, when IC is equal to 0. So, when IC is equal to 0, it simply tells us that there is no current flowing through the transistor. It looks like an open circuit, okay? It looks like an open circuit. So if I were to measure the voltage, between the collector and the emitter, it simply tells me that I will get the same voltage which is equal to the supply voltage, VCC. So it simply tells me that when IC is at 0, VCE shall be equal to VCC, the supply voltage. Okay, now, going on, let's look at what happened when VCE is 0. It simply tells me that I have a maximum current flowing here IC such that this transistor looks like an ordinary conduction wire. So, in that case, when VCE is equal to 0, IC will maximize. So IC will be maximum. So I need to determine the value of IC maximum when we say it's saturation. Remember, we don't need to drive the transistor to above saturation. It is no longer an amplifier for that. So we need to be careful of the maximum collector current that can flow before the transistor can reach saturation. We have to avoid the transistor from going into saturation. So, now, when IC is 0, VCE is equal to VCC. When VCE, our voltage across the collector and the emitter is 0, IC is maximum. So, how do we determine the value? It simply tells us that for us to find IC saturation, IC maximum, so that we don't drive our transistor to beyond its value under amplification. It simply tells us that the current that shall flow here maximally shall be given by VCC over RC. So now we know that the first step to identify is the maximum current that will be permissible in the collector terminal, which is given by the value of VCC, supply voltage, all over RC. Why are we saying that? We know that when VCE is 0, IC maximizes. So for us to find IC maximum, it simply tells us that VCE during that point shall be equal to VCC. So it's VCC over RC give us the value of IC. So now in our output characteristics, we now know one value. Let me just erase everything like this. In our output characteristics, this will be our IC in milliamps, this is our VCE in volts. So we now know point, let me call this point C. We now know point C, which gives us the value of IC maximum. We've already calculated. We now know our IC maximum. And mind you, we're saying when IC is 0, VCE shall be equal to VCC. So somewhere here, we shall have VCC, which is equal to VCE. So these two will help us to plot the DC load line. Remember, we said it's the line that characterizes the transistor values during operation when there is no external signal. So we shall call this point D. Let me call this point D. So now I will take my ruler and join these 2 points. In that way, I have actually now drawn what we call the DC load line. It's as simple as that. It's not a heavy task. Let's look into a typical exam question, which will lead us to be able to draw a DC load line. I will simply slot values into that so that we don't have to redraw this. I'll call it figure 1. If RC, if we've got a VCC, let me say a VCC of 12 volts. We've got a capacitor, a resistor which is 12 kilo ohms here. We've got RB equals to say 100 ohms. Let me just, for argument's sake. Now, the question will come like, let me just write here. Determine the values of IC and VCE that will enable you to draw the DC load line of the circuit in figure 1. Okay, and then maybe they'll write 5 marks. Okay, so the solution. Let me erase this. Okay, the solution. The solution is simple. Now, let's write solution. So remember, for us to draw the DC load line, we need to go back into this. Let's look at the output. For us to find I saturation, IC, let's start with IC. We have said that IC can be given by a value which is equal to VCC over RC. What is the value of our VCC? VCC is given to be 12 volts. Okay. What's the value of RC? RC is given to be 12,000 ohms, or 12 times 10 to the power 3. 12,000 ohms. This gives us something like 1 times 10 minus 3, which is 1 milliamp. So it means in this circuit, a maximum current of 1 milliamp must flow into that. So I may now start plotting my graph. Remember, IC, let's say in milliamps. So it means my IC in milliamps will simply write here 1. I can simply say 0.5 here. Now, looking into that, remember we say for us to determine VCE, we must look into IC at its minimum. So the maximum voltage that can be achieved across VCE is equal to VCC, where VCC is what? 12 volts. So it simply tells us that our VCE shall be equals to 12 volts, which is equals to VCC in this case. So here I may safely write 12 volts. So now I have point C and D according to my calculations. So I can now be able to draw the load line, as simple as that. Okay, obviously you'll be using a ruler when it will match straight. So that is one typical exam question which might come and you might need to do that. You just need to remember this. Okay. There is also in designing amplifiers what we call the operating point, which is also known as the quiescent point, sometimes denoted by Q. What is an operating point? What is an operating point? Sometimes denoted by Q. So, another important point is what we call the operating point. Operating point of a transistor. Operating point. It is denoted by Q. Q for quiescent, sleeping. They normally say sleeping. So we normally call it Q. So it's a certain point along the output characteristics. It can be chosen anywhere along the load line, which we've shown. It can be chosen anywhere along the load line, depending on the application of the device, on what you want to do with the device. So you can choose any point along the load line, so that your amplifier can operate at a certain class, or you might call them classes of amplifiers. For a transistor to operate as an amplifier, it is normally chosen to be right at the middle of the DC load line. So now, you have your DC load line, you have your IC, you have your VCE. You have your VCE here. You have your IC there, you have your VCE there. So this operating point, remember we say this transistor will operate along this line. So we can choose any from here to there. Anywhere along this line, we can choose our load or quiescent point, our operating point. So we say for an amplifier, audio amplifiers, current amplifiers, we normally choose it at somewhere along half of VCC, somewhere here. So we normally choose it somewhere there, Q. Normally, it is chosen at the middle of the load line, which is equal to half of VCC. So now that I've added this, let me give you another task so that you can be able to tackle these examination questions. I am adding bit by bit so that you can understand. I didn't want to give you everything all at once. We talked of the DC load line, now we talked of the operating point. Let's see typical exam questions which might be aligned to those two, which is the DC load line and the operating point, and how do you plot them in your answers. I'll have another amplifier which I shall call figure 2. We still have RC here, we have RP there. Let me just leave those components there. RP, RC plus VCC. So we are saying if our VCC is 30 volts, let me just set it at 30 volts, and RC is 5 kilo ohms. So RC it's 5 kilo ohms again. RP 1.5 mega ohms. Yeah, that much peak. And we also have the beta gain of this amplifier to be set at 100. Let me call this figure 2. Okay, so for now, or for figure 2, you will also be asked to draw the load line and plot. Yes, draw the load line and plot an appropriate quiescent or operating point using all these given values now. Okay, so where do we start? Here. Let's start the solution. Or actually, I write down the question. It says, draw the DC load line for this circuit. Draw the DC load line and plot an appropriate Q point with given values above. Now, let's see. Where do we start with the solution? Remember, we need to draw a DC load line. Let me start with the calculations. For us, we need to find I saturation. It says so. We need to know IC saturation. So we are saying IC saturation is equals to VCC over RC. In this case, it will be 30 over 5 kilo ohms. Kilo, we all know by now that we multiply that by 10 to the power 3. And that will give us a value of 6 milliamps. Good. Now, the other part, VCE, we now know shall be equals to VCC, where our VCC is equals to 30 volts. We can now draw the DC load line. So, let's draw the DC load line. There we are, IC in milliamps, VCE in volts. So, let's say 1, 2, 3, 4, 5, 6. So we have our 1, 2, 3, 4, 5, 6. VCE being 30, 15 here. Let me just say 7.5, blah, blah. So, now, we are having these two. We can now say VCE is 30 and IC is 6 milliamps. And then we draw our DC load line with respect to that. So, first step, DC load line, draw. So, how do we plot an operating point? Remember we said an operating point is somewhere along VCC, half of VCC, isn't it? So, but before we go there, we need to find what we call IP quiescent. That is IP according to Q. IPQ. So for you to find IPQ, you need to know the value of your VCC and the value of your VPE, where we say IPQ is equal to VCC minus VPE, all over the value of the resistor at the base. So you will notice that you know your VCC, but you don't know your VPE. Okay. Some textbooks or some examiners will tell you the value of VPE. Some will not tell you. So, if you are not told, you always assume your VPE to be equals to 0.7 volts. We all know why we choose 0.7 volts. We know that semiconductor devices, they will start to conduct, more especially silicon, they will start to conduct at a value of 0.7. So now, knowing that, you can now say VCC, which is 30 minus 0.7, all over, what's the value of that? 1.5 times 10 to the power 6, is it mega? So we now know that if you punch your calculator, you will get a value of 19.53 microamps. We now know IPQ. This is our Q point, isn't it? We now know IPQ. We now need to know ICQ, where we shall say ICQ shall be equals to half of VCC, or we shall say, we can use this formula where we say it will be beta times IP at a quiescent point. So remember, we are given beta to be 100, and we found IPQ to be 19.53 times 10 minus 6. This will bring our value of ICQ to 1.953 milliamps. If you punch your calculator, loads of indices. So now we now know that for Q in IC, it will be 1.953. And for Q in B, it will be 19.53 microamps. So, that being said, we can now simply say we have IPQ, which is there. We have ICQ, which is there. So in that way, you are able to plot and draw your DC load line. We have more examples, but for this lesson today, we shall take it to this end. So if you are not clear or you want more clarity on this, we shall meet in our Ehlanzeni college.co.za page, or you can also go to our Facebook page and our Twitter page with the hashtag of Ehlanzeni College. So thank you for today, and thank you for having me or giving me your ear.